All right, ladies and gentlemen, I think we're ready to go here now. Okay, so far, what we've investigated is this base angle theorem about isosceles triangles. We're also going to talk some about equilaterals today. But the first thing I wanted to get down into your notes, just so we're clear, is a little bit of vocabulary again about isosceles triangles, because the different angles and sides on there, they have different names, kind of like the base angles like we already talked about. So I'd like you to draw a triangle that looks pretty isosceles, something maybe like that. And we can go ahead and label on here where the congruent angles should be, where the congruent sides should be. And we already discussed it, but the two angles are called base angles. And what do you suppose that this side of the triangle between the base angles is called? Yeah. Or just the base. Yeah, just the base. Could call it a base segment, I suppose. But just refer to it as the base, and that's fine. Okay. Yeah? Mm-hmm. Now, the other two congruent sides are called the legs. Kind of like, shh, quiet please. It has to do with the fact that there are two of them, yes, and it's kind of like what's holding the triangle up. You can think of it that way. And then the point up at the top is called the vertex. Now, it's not always at the top, because sometimes these are like, sitting on their side or whatever, but that point that is not one of the base angles is called the vertex, and then the angle that is there is called the vertex angle. Yeah. Okay, so if I give you like some information about an isosceles triangle and I put it in words and don't actually draw you a picture, if I use any of these terms, this is what I'm referring to, okay? So if I say the legs are each 2 feet long or whatever, or if the vertex angle is 36 degrees, you should be able to tell me what's going on the rest of the way, okay? So let's play around with that a little bit. So let's say the vertex angle of an isosceles triangle let's say it's 44 degrees. So find the measures of the base angles. So based on what we just talked about, then, how do you suppose you could go about doing something like this? If you know the vertex angle, how do you find the other two base angles? Yeah, Zach?
Well, don't all angles have to add up to 180 degrees?
That's a true statement, yeah.
So do you take 44 and minus 180?
Okay, so let's start with that. So 180 minus 44, and what does that get you? Yeah? 136. Okay. Right. So what we basically did with this step is figure out, okay, if we take away that 44 degree angle, how much do we have left over? And the two angles that are left should be the same, so if we divide that up by 2, then it should be the same for each of them then. So 136 divided by 2, each angle should be 68 degrees. Mm-hmm. And you can double check that if you'd like. You know all three angles are supposed to add up to 180, so you can go 68 plus 44 should be 180 then. Okay? Something like that. All right. Let's try another kind of example involving these guys. How about... I'm working on it. Okay. So there's your picture. I'll give you a second to jot that down, and then I'll scoot it over so you can see the rest of it a little clearer. But basically, we're going to try and apply this our base angle theorem we just talked about. And this is going to kind of lead to the converse of that as well, which is not anything majorly different. So basically, we want to try and identify an isosceles triangle in there based on the information that's given. Okay. Now each of these two statements are standalone. One doesn't go with the other. Okay. So if we ignore everything else, and all we know is that angle A is congruent to angle D, what else do we know about the picture? So let me maybe get that in there so you can see it. Okay. So if angle A and angle D are congruent angles, what do we know? What?
Do you mind if we put that in the triangle quick?
You. So we're saying this angle and this angle. Yep. Yes, sir?
Then angle ABE is congruent to angle DCE.
Not necessarily. No. Savannah? That's right. Okay. Let's talk about that for a second. If A is congruent to D, if these two angles are congruent, do you see how this then, the big triangle around the entire picture, would be our big isosceles triangle then?
Yep.
And if that's the case, where are the two sides that are supposed to be congruent? AE and DE, right? That's what that's saying. Okay. All right. Now the next one, if AB is congruent to, so AB would be here, and BE is here. Okay. Now ignore if the picture maybe doesn't look quite to scale there, but if we know those two segments are definitely congruent, then what else do we know about the picture, Seth? Not necessarily. Again, we don't know that these are congruent anymore. These are two completely separate questions. Okay? So all we know is AB is congruent to BE. That's all we have to go on. So what other things can we say are congruent on this picture then, if that's what we know? Jason? Nope, we don't know that either. Because we know nothing about those other lines over there and what angles they make or any of that. Yeah? Yes. Yeah. So, do you guys see the isosceles triangle in the picture now? It's this one. It's been turned, right? Like I said, it doesn't look like it's been drawn to scale necessarily, but if these two are congruent, this is the isosceles triangle then, this ABE, right? And if that's the isosceles triangle, where are those congruent angles? Here and here, right? Angle A and angle, well, technically we should say AEB, right? But these two angles are the ones that are congruent then. So that's what's going to answer. So angle A is congruent to angle AEB for that one. Okay. Now, one of these two questions that you just answered, you used the base angle theorem, and one of them technically you didn't. Which one of those two questions did you use the base angle theorem?
The first one.
No.
Oh.
No. Let's go back. Sorry. Let's go back to the base angle theorem, what it says. It says, in an isosceles triangle, the base angles are congruent. What makes something isosceles? Sides or angles? Sides. So this could have read, if two sides are congruent, then two angles are congruent, right?
That was a trick question.
Not really. So if the sides are congruent, then the angles are congruent. To see how this one I was using it? This one up here, if the angles are congruent, then the sides are congruent. That is not technically the base angle theorem. That is the converse of the base angle theorem. It's also true. Yeah. It's also true, but it is technically not that theorem 5-6. So let's jot that one down. If you have your theorem sheet ready, you can put this right on there. So this should be the converse of the base angle theorem. So if two angles are congruent in a triangle, then the sides opposite them, just write it down, are also congruent. And so this one, the picture is going to look pretty much the same as the last one, but it's all about what you're starting with and what you can conclude. So this one, you're starting with the fact that the angles are the same, and then that tells you that the sides must be the same. And in the first one, it says if the sides are the same, right? Two angles, two sides, they should all be there. It doesn't matter which way you go, really, because both are true. But technically, each is its own little theorem. We're going to come back to some algebra ones, but I want to talk about equilateral triangles first, get that out of the way, because then we can do a lot more with it. And this is all stuff that you guys already know, so it shouldn't be too tough. Equilateral triangles. Just so we have the properties in your notes somewhere here, we're just going to jot it down. You may. Alright, so every equilateral triangle should have three angles the same and three sides the same. And that's pretty much it. Now there are some corollaries in your book, and corollaries are kind of like an extra little something that relates to a theorem that you've already learned about. And the two little corollaries that are in your book, they just say, if a triangle is equilateral, then it is equiangular. And there's another one that says, if a triangle is equiangular, then it is equilateral. But that's all kind of stuff we've talked about already. Okay? So basically it just boils down to the fact that all these should be the same and all those should be the same. And if all the angles are the same, then we know 60, 60, and 60. Okay? Don't forget that, because that will be helpful kind of down the road with some of these problems we're going to look at coming up. Okay? So let's see if we can put some isosceles and equilateral triangles together in some little pictures. We're going to throw some algebra in there. And can we solve for x and y and that sort of thing? And if things look good there, then I'll let you guys get into your homework at that point. Okay. So let's say we got that triangle. These two triangles next to each other. Does it? Wasn't meant to be, but okay. All right, so I did a little x, y, and z on this one. This thing probably looks more confusing than it actually is. If you just pay close attention to what's supposed to be the same, where are there some angles where you already know what the angle measurements are supposed to be, it's not too terribly difficult. Okay? So let's start with x. X is an angle that is sitting in what kind of a triangle? Yeah. Equilateral. So, somebody else? What is x? Yeah. 60 degrees. Boom. Easy. Got it. Okay, so we know x is 60 because it's in that equilateral. Okay, now let's jump to y. Y is not an angle, y is a side. Okay, so does anybody see something in that picture that might help us figure out what y is, dear? It has to equal 40, okay? Or at least this whole expression has to equal 40, right? This is equal to that, okay? Because those are congruent sides, okay? So 40 equals 2y plus 10. And then we can work that out. So subtract the 10, 30 equals 2y, divide by 2, and y is 15. Okay. Now this z. Z is an angle that's in the other triangle, but what kind of triangle is that one? Yeah. Isosceles. And it is one of the what angles? Nope. Yeah. What is it, Nolan? Base angle. Yeah, it's one of the base angles. Okay. Now, I can't find a base angle unless I know either the other base angle or the vertex angle. But if I know either one of those two, then I can do it, right? Yeah. We already proved that with the last example that we did. So the angle at the top of that triangle, the vertex angle, it says x. So how many degrees is that vertex angle then? Yeah. It should be 30 then, because we know x is already 60, right? So if this is 30, then how can we find z? Yeah. Okay. So kind of like we did before, right? If we know the vertex angle, subtract it from 180, that's where you got the 150. Divide that by 2, and one of the base angles should be 75 degrees. Yeah. So I'll just do it like this. 180 minus 30 is 150. So then 150 is equal to 2z. These both should add up to 150. And then if you divide by 2, z is 75. Good. Okay. So it's that kind of stuff that you're going to be taking a look at. I think you guys are fine. I'd rather you guys just get right to it here. So, yeah, we'll leave it at that. Call it good. I'm serious.